right. Okay, so let's try that again. You ready, Peter? So I'm going to throw this ball, throw it back, right? And now, when we do this thing, when I throw this ball, most of the time you think of it as translation, agreed? It's going from one spot to another. Now, if I could do that trick where you spin the ball on your finger, right, you would have pure rotation, but, or you might say, well, you can throw it with some spin, true. But even if I throw it with zero spin, my claim is you can view it as having this new property called angular momentum. Now, I have a simulation to try and show this because it's really difficult to explain. I hope this simulation helps. Oh, lights. Okay. So the idea here is this. Okay, I've got this code here. Let's just run it and watch it. And I need to, I think, just forget that for a second. Watch the code. Notice there's an object, a pink sphere that's moving. And it's moving kind of along that line. Do you agree? That's not the line of action, though. That's just the line of motion. It's a little bit off, but it's pretty close. Let me see if I could draw that a little bit better. There it is. There's a line through the motion. I'm going to call that the line of motion. This is different than the line of action. Can you see that out here in class as well as on Zoom? All right. Now, I noticed that somewhere at random, it's a little bit hard to see here, but right here is a pivot point. There's a pivot point right there. And what we see here, this is the velocity of the ball. And this is called the R vector. Notice it's from the pivot to the object. It's very similar to torque, only instead of force, we're using something that relates to velocity here. Let me run this again so you can watch this. Notice the R vector is there. The velocity is along the line. I didn't spell motion right. Oh my gosh. Whatever. There's an O in there now. Sorry. The angular momentum is given by a quantity. Let me write it here. L is this new quantity called angular momentum. I'm going to call it ang-mom. It's equal to a cross product between the R vector and the momentum. Now, when I say momentum, I mean linear momentum. So I might write that another way. It's a cross product between this weird R vector and mass times velocity. That's the angular momentum of a particle. And this is all described in gory detail on page 83, and we're going to do that again. But I wanted to give you a visualization. What direction is the angular momentum here? It's a cross product. That first R looks terrible. I got to clean that up. It's driving me nuts. When you're doing a cross product, how do you do the right hand rule? Your hand lines up with the R, or the first vector. You curl to the the velocity or the momentum in this case, or the second vector. And what does the thumb tell you? Into. See that white arrow there?
That's an arrow. I couldn't figure out.
I know, I was hiding it. That's the big reveal. Oh man, this is amazing, right? Does that make more sense now that you can kind of see the arrow? So, right, from a pure side view, you don't really notice it that much. But the idea is R cross momentum is into the page. Is everybody okay with that? Now, I'd like to stop this. Any questions? Okay, let's get to the board work now, and let me clean this up. Alan, can you get the lights for me while I do this stuff? I really appreciate that. Thank you.
So there's not any coding in the next exam.
That's right. I'm not going to do any coding questions for you. It should be the top 3 up. Yeah, for this class, since I'm live streaming and there may be students in a future class, I got to be clear. For spring 2022, there will not be a coding question on test 3 or the final. Good. But for future years, if you're watching this in some, you might. There. I love how I'm able to taunt my future students. Whatever. All right. Good enough on that? Yeah, yeah. Okay. I want to go through page 83 as fast as possible. You've got your notes. Please watch me on the board and we'll learn about this. So let me get on the right whiteboard. I like that marker. This one's no better. Come on. Good enough. Right? And this is true for a point particle. Okay? R is from the pivot to the particle. Right? P is equal to the particle's mass times its velocity. This is sometimes called, now that we have more than one type of momentum, there's going to be angular momentum, which is L, and this one is sometimes called linear momentum. Sometimes it's also called translational momentum. Okay? Now, in practice, there are several tricks shown in your workbook. I want to at least show you one of them. So in particular, we need to have a pivot. Here's a pivot. Geez, where's this red marker been all day? Frickin' A. There's going to be some vector R, and I need you to label this the same. Well, this is the trick. You don't need to label this. You can just watch. And then there's the velocity of this particle here, or its momentum, P. I'm going to draw what's called the line of motion. Notice that's not the line of action. Line of motion. And just like in torque, you could do what's called R perp. You draw the perpendicular bisector. So there's a right angle. That's what I mean by perpendicular bisector. I draw a line from the pivot to the line of motion, which intersects it at a right angle. That's the perpendicular bisector. This side is called R perpendicular. Now, usually there's some angle involved here. Notice this angle right here. How do I want to do this one? I don't know if I want to draw it that way. Let me check my notes and see. Yeah, I don't want to draw it that way. Let's do it. Actually, I could do it this way if I just draw right here. This will be fine. Let's say this angle is the angle between the r vector and the line of motion. Do you agree this is also that angle theta right there? And that'll get the job done. So I'm going to point out something up here. If I bring this up to my original definition, we can actually figure this out in a couple of different ways. We could say it's the radius times the momentum times, geez, I need another color. I'm going to put this theta in black, okay? So it stands out a little better. Times sine of the angle between. Or, do you agree that r perp is r sine theta? There's a right triangle here. It turns out you could just get the perpendicular distance times p. At first, you may be saying, that's stupid, dude. Why don't I just do this all the time? Yeah, that works. It turns out in practice, this term, r perp, is actually easier to deal with in most scenarios. So at first, you're like, why not just do the r vector and do a cross product with ijk? No, just trust me. This perpendicular distance, I'll call it r perp, is sometimes called the impact parameter. Okay, so that's what r perpendicular is. In practice, that it's like a lever arm for torque. It makes angular momentum problems easier. Questions about this stuff? You see how r perp is just r sine theta grouped into one? What's interesting is, as this particle moves, do you agree the radius is going to change? Do you agree the angle is going to change? Do you agree r perp does not? R perpendicular is the quantity that does not change as the particle goes flying by. That's why it's easier to deal with r perp than r sine theta for some problems. This is often a constant. Neither one of these is. Brutal. Enough on that? Now, I feel really uncomfortable right now about something that I've written right here. Why do I feel uncomfortable? Vectors. Do you agree this is a vector and these are not? How do you get the direction? Do you remember what I did when the simulation was playing? How do you get the direction? So strictly speaking, these equations are for the magnitude of angular momentum and the direction you get from doing this crap. Is that good? And what about for, let me see, is there anything else I want to say on that? I want to point out, notice if you plug in MV perp here, L is going to be equal MV R perpendicular for a point mass. So for a point mass, usually we're going to use MV R perpendicular and get the direction with the right hand rule. For distributed mass, like a disc, a rod, a sphere, crap like that, I could get angular momentum a different way and much easier way. If you recall, linear momentum was mv. What's the rotational equivalent? What's the rotational equivalent of mass? I. Yes, moment of inertia, I. What's the rotational equivalent of velocity? Omega. Could you do this for a point mass? What do you think? Is there a moment of inertia for a point mass? Yes, you could absolutely do this. So this is valid for point masses as well. Most of the time we're going to use this. In rare cases, we need to do it this way, and I will show you those in a minute. You have to trust me. Every once in a while, you need this. Okay. And then I want to talk about 3 important things in physics. Do you agree we have a concept called conservation of energy? Just humor me for a minute. You don't need to write this shit down. We're going to review it next time. Just listen. What does conservation of energy mean? What's the equation? When I say conservation of energy, there's an equation that I mean. We used it once today. For rolling down the hill. Energy initial equals energy final. Does that make more sense now what I mean about the equation? And there was like K plus U equals K plus U. But in order for this to be true, there was a special condition which applied. If what had to be 0? Work. Huh. Didn't we have another conservation law in chapter 9? Conservation of momentum? What would that look like in equation form? What's the letter for momentum? And maybe I'll say it this way, momentum linear. Yeah, it was P. So what does it mean for momentum to be conserved? In order for that to be true, there was a condition, right? The external forces had to be 0, or they had to be balanced, or the collision time had to be so short that the external forces were negligible. Huh. Where do you think I'm going with this? There's conservation of angular momentum. I've kind of run out of room on this board, so I'm going to write it up here on the next board. Gosh, that sucks. I'm going to squeeze it in here. I apologize. Can you guys see over the monitors if you have to? We're going to review this next time. You can have conservation of angular momentum. Well, what would be the equivalent equation I could write? L initial equals L final, but that's not always going to be true. It will only be true if what? Sum of external torque equals 0. Are you starting to see some patterns here? Isn't that cool? We now have a number of tools. This is a big picture review of the entire class to date. If the acceleration is constant, we use the constant acceleration kinematic equations. If work was 0, we could do an energy equation. If external force was 0, we could do a momentum equation. If external torques are 0, we could do an angular momentum equation. We're seeing that to use a tool from the physics toolbox, we must check if the correct condition applies. Isn't that cool? We're going to be able to do problems now, and you could say, you could look at the problem, and we're going to practice this next time and say, which of these conditions are valid? Which equations can I write down? And then which algebra do I do? That's basically this class. Can you correctly grab the equations and use a few tricks? All right. If it helps, right, let's go to the other board real quick. It turns out this conservation of angular momentum usually takes on, okay, star, we require the sum of torques external to be approximately equal to 0 for this to be valid. Sometimes it's not exactly equal to 0, but it's so small it's negligible. Okay, and then we could say I1 omega 1 initial plus I2 omega 2 initial is equal to I1 omega 1 final plus I. You see that's basically chapter 9 again, but with I's and omegas instead of M's and V's. What do we have to be careful with when you do a momentum problem from chapter 9? Momentum is a vector. Watch the plus minus signs. Some things could be rotating positive or negative, right? You could have a positive rotation or a negative. Said another way, on every single term here, there's an implied k hat usually. Did that make sense? Or there's some rotation axis implied. These omegas are actually velocities, not speeds. Angular velocities, not angular speeds. Or, as crazy as this sounds, let's see if I can do one here. I want you to watch this 2x4. It's just sitting on the floor. You agree it started rotating? That's another way to do it. You could say M V R perpendicular for the basketball equals initial equals M V final times R perpendicular for the basketball plus I of the rod, omega of the rod. Let's run that again and see if that makes sense. The pivot point is the floor. R perpendicular is the distance between the floor and where the ball makes impact. Omega of the rod is its RPMs as it twists over, right? And in this case, there's a V initial of the ball going in and a V final coming out. Hey, we didn't turn off the machine. Got it? Isn't that cool? I don't know, I think it's beautiful. I have a strange sense of beauty, but whatever. Okay. Pretty cool, right? I know. I get excited about this chapter. Those are listed at the bottom of page 83, right? You can do I omegas, you can do MVRs. Basically, you're going to have some combination of this, right? The initial rotation rate of the rod was 0. Instead of using I omega for a point mass, I subbed in MVR perp. Same problem. Okay. Now, look at the very, very bottom of page 83, especially if you're a CS major, right? To do this in a code is pretty simple. instead of getting force, then momentum, then position, you get torque, then angular momentum, then change the angular position. And that's how you make things rotate in a code. That training video I sent you will walk you through the practical aspects of implementing the vector notation in a code. You do not have to do that this week. It's an option. So those of you that hate the coding, don't do it. You'll do a regular lab. Those of you that are CS, I think you'd be crazy not to learn how to do this, because you're going to have to do this someday, right? Learning how to use rotation vectors seems like a pretty straightforward thing to learn, and something you should learn as a CS major. How to rotate something? Come on. Seems reasonable. All right. That's the summary. The rest of class today, we're going to do a couple of examples. I think we can get 2, maybe 3 in. And then next time in class, more examples. Got it? In particular, I'm going to practice a lot at the end of next class on this, because my pet peeve is when students grab an equation inappropriately. So we're going to practice this a lot. I'm going to give you different scenarios, rapid fire, and say, can I use these equations or not? So we're going to practice that next time. That said, start looking at 11.1 on page 84. I'm going to erase the board. 11.1. I like that 2x4 in basketball demo. Did you guys? I've never done that one before, but I think it works. It gets the point across. I hope. Talking with somebody today that was talking to a former student that's like an MMA fighter in the amateur leagues. Right? All this stuff is in MMA too. Like it's in baseball. It's in all kinds of sports. All of this motion. If you're into sports and that can somehow make you interested in studying this or find a reason to appreciate it. I mean, all of the moves that you make as an athlete relate to physics. It's all straight physics. And then a lot of practice and talent, which I don't have. Okay, 11.1. We're going to have some orbit. I think there's, what is this? A moon and a planet. So there's a planet, then there's a moon. And we're going to call this point A. And at the center of the planet, we're going to call that point B, just to simplify our writing. Okay? So B at center of planet. And let's assume this is really far away from everything else. We're going to ignore all other sources of forces. It's just the moon and the planet somewhere way out in the middle of nowhere. Okay? Keep it simple for now. My claim is we can get the moment for the angular momentum, right? Oh, and what did I say? This radius is R, is that right? Okay. And I want to read here. Moon has mass M. Moon mass M, speed V. And I'm going to say constant speed V. Okay, so this is going with constant speed V. Part A. I want the angular momentum about point A. to be clear, what do I need? I need the radius from point A. And I need to cross that with the mass times the velocity, right? And then if you could indulge me one extra weird little notation here, we're going to do this again in part C. So I want to call this L initial, okay? So it's the initial angular momentum about point A, because later on we're going to talk about the moon at a different spot. To be clear, let's assume the moon's traveling this way, V. Okay. What is radius RA initially in terms of the radius of the circle and a unit vector? What's that equal? How far is it from, it goes from what to what? When we're doing angular momentum, I go from blank to what? Remember the definition?
From pivot to blank.
From the pivot. If you could only remember two words, from pivot, from pivot, from pivot. Is that true in torque or angular momentum? What's the distance from the pivot to the moon? Not r squared. You're close. What's the distance from here to the other side of the circle? 2r. You said r squared. Yeah. 2r. And then what is the unit vector? If I'm going this way, what direction is that? Usually. What do we usually call this direction? I hat. This way is usually. What way is K hat? Into the page or out of the page? I goes to J goes to K hat is out of the page. Okay, so this is from here to there. The distance is 2r. What direction? Positive. From here to there. What direction is that? I have. Do you agree? I think you guys are tired, right? You guys are better than this, but you're just tired. Oh, okay. I'm not trying to torture you. Sorry, my bad. Once we do this first one, the others will be easy. MV. What direction is the velocity in this picture? J hat. All right, there you go. You were just tired. Now, when I run this, do you agree it's going to be 2 RMV? What is I hat cross J hat? Remember the wheel of pain. Isn't that better than doing a frickin' matrix? Come on. Don't do the matrix unless you have to. I goes to J goes to K. You just did your first angular momentum calculation. Not bad, right? Let's do about point B. Let's do L about point B initially. And I think that's what I want to do, right? Yep. Oops. Okay. Yes, question?
So in the first problem, our pivot was around point A.
Yes. Oh, okay. Oh, I see what you're saying. And maybe I didn't make that clear. I apologize. I think it was, so I said, let's get the angular momentum about point A. Now here's the deal. You raise a good point. A is not the logical point to choose as the pivot. Do you agree? It turns out this is very different than torque problems. You can always choose whatever pivot you want. The point of this problem is to show that this is a terrible choice of pivot and this is a good one. So strictly speaking, when you're doing angular momentum, you get to choose the pivot point wherever you want. And that's my fault for not making that clear. Okay. All right. So now you want to give how many with this one? Now I'm going to choose B as the pivot point. So I want to get the angular momentum initially about point B. What's the R vector?
Positive I.
That's correct. So I go R in the I hat. I'm going to cross that with MV in the J hat again. So notice here, I get R, MV in the K hat. Agreed? Now, let's have point B remain the same. Let's have point A remain the same. But the moon is now in a different state in its orbit. Let's say the moon is now up here. It's moving with constant speed v. It's at a different point in the orbit. What is the angular momentum in the final state about point A? And notice the order of the subscripts, who cares? Well, it's going to be radius in the final state for A crossed with MV. Well, in the final state, what is the radius vector from A to this point? What is that? How much in the I hat? How much in the J hat? How much do I go over? R, how much do I go up? So it's going to be do you agree? Some in the I hat, some in the J hat. What's my velocity vector now? What direction is the velocity in this state? Negative I hat. Which term will not survive upon doing the cross product? Which term will gives us a 0 in the cross product? Is it I cross I or J cross I? Yeah, I hat cross I hat gives you 0. So now this term is going to drop out and we're going to get R, M, V, J hat cross negative I hat. Can I factor this minus sign out to the front, please? There's a minus sign from here. There's an RMV, and then cross product, you got to keep the order. J cross I. What's J cross I? Negative K hat. Notice that this minus sign will cancel this minus sign, and we get RMV K hat. Finally, let's do one more. L final state B. It's going to equal R final for B crossed with MV. What's R final for B? RJ hat crossed with MV negative I hat. What are you going to get when you do this? Negative RMV J hat cross I hat. What do you get? What's J hat cross I hat? Negative K hat. The negatives cancel. And so here's what I wanted to point out. when you're doing angular momentum problems, you get to choose the pivot. Which choice of pivot seems easier? Is it A, where the angular momentum changes? Or is it B, where the angular momentum doesn't change? Gee, I wonder. Just because you can choose any point you want doesn't mean you should be stupid about it. You should pick a pivot point in a problem that seems like the logical one, which is what your intuition told you, which was excellent. In general, just because we could use point A doesn't mean it's a good idea. If there's a pivot point in a problem, use the pivot point. Enough said? That means, but if there's weird cases where you could solve problems by choosing a weird pivot point. Enough on that. We got 5 minutes. I want to go into the impact parameter, 11.2. 11.2. So rather than doing the full vector every time, I want to learn how to use this impact parameter, R perpendicular. So imagine we have a rod here and a pivot point, and there's a ceiling. We're going to take a point mass here and throw it at it. And I believe in this problem, we're going to say this distance right here is X. I'm going to say this distance here is D. And I believe this mass has mass m over 2 in the problem, and this has speed v. Yes. What up, Dom? And to be clear, this is like our 2x4 in the basketball, or it could even be it's like a golf ball. Here's a rod with a pivot, right? And I'm going to eventually, somewhere, I've got a golf ball with Velcro that we could stick onto this, and I lost it. But the idea is there's going to be a ball that's going to come and hit it like this. Okay, got the visual? Probably under that roller box there. Now, in this case, does anybody remember what the impact parameter is, or what the R vector? How about this? Let's start with R vector. What is the R vector? From what to what? From pivot to the particle that's going to have an impact. Do you agree this is going to impact? This is the R vector. In order to get the impact parameter, I need to draw the line of, you remember what that was called? The line of motion. It was line of action for a force, line of motion if it's through the velocity vector. Notice in this case, I need to draw a perpendicular bisector. Just watch my finger for a second. Is this the perpendicular bisector that I'm drawing right now? Yes or no? Does it intersect at a right angle? Does it intersect this line at a right angle? Is this the perpendicular bisector? Is this?
Yes.
Yes. So in this case, that distance is the impact parameter, R perp. For this particular case, what value does it have? R perpendicular equals X or D? R perpendicular equals D. Excellent. I'm going to show you the angular momentum calculation. L is going to be M V R perpendicular. Now we got to be careful here. Watch this carefully. I want the L of the point mass about the obvious pivot. Is M the correct mass to use? I need the mass of the point mass. Is that M? It's M over 2. So I got to use M over 2 because that's the mass of my particular point mass. Is the speed V? Yes. What is R perpendicular? In this problem, it is D. Got it? That's how you could use the impact parameter. Now, here's where I was saying you might want to leave, but I'm going to go ahead and keep cruising and just at least get the impact parameter for 11.3. If you can stand it, I encourage you to stay. If you can't, I understand. It's the same problem. And remember, you can watch the video later, but seeing it live is probably going to help you. Apologize for running late. Now what I want to do is I'm going to say the entire length of the rod is D. Okay. And now I'm going to have the point mass over here. I need a little bit of space. Now my particle is going to be over here, distance D. This figure is not to scale. We're told that the distance here is also D. And one last piece of information, we're aiming this particle right at the center. Okay, so there's the velocity. Now, all I want to do is get the impact parameter and call it a day. We're trying to get the impact parameter and call it a day. See if you make sure you watch the vid later, okay? Or just look at the solutions. This is all in the solutions. In this case, I need a perpendicular bisector. Okay. So to get the perpendicular bisector, I draw the line of motion. Is this a perpendicular bisector? Straight down, yes or no? Is this going to be a perpendicular bisector? How about this? What's that? No. Do you see it's right here? You see that right angle? That is going to be R perpendicular. My claim is you can relate R perpendicular to D. Okay? We want to relate R perpendicular to D. Dang. What's that? No, it's different than that. And that's why I wanted to show you this. This is a new style. If you're a civil engineer, if any engineer, learning how to do geometry with triangles is important. So let's try and get this right. Do we know this angle? Yes or no? How about this one? Crap. Do we know any dimensions here? Do you know any sizes? Do I know this side of this triangle? What is it? Okay. So this side's D over 2. Agreed? Do I know any other dimensions in this picture that are not labeled? Look at this triangle. Do you see a triangle down here? Do you see any dimensions in that triangle? What's that? Yeah, what's the bottom part? Not D. It's just half of it. Do you agree? From here to the bottom is not the full D. It's D over 2. Wait a minute. Look at this. Which one of these triangles is going to be useful for starting the problem? The top one or the bottom one? Why? What can you get from the bottom one? Angles, if you needed it, right? Do you agree? We know this side, we know this side. Could you get this angle right here? Could you get that in theory? What would you have to use? So, cut, or TOA? TOA. So tell me what tangent of theta equals. A tangent of theta equals. What's opposite? Do you agree that's just 2? In theory, we know tangent theta is 2 now. Isn't that cool? You agree you can figure out the angle if you needed it? Why is that useful? Help me. What can I do next? This would be theta. Can I now relate d over 2 to r perp? Would I use so, cut, or TOA? Where's the right angle in this one? This is the right angle. So where's the hypotenuse in this triangle? D over 2. So would I use so, cut, or TOA? So I really appreciate the extra time. I swear I'm stopping right as soon as we get this. That's going to be what? R perpendicular over D over 2. Do you agree, in theory, we know what theta is. You could plug theta in. You could get R perpendicular in terms of D. So this is a more difficult, whatever you call it, impact parameter. We're going to do more examples next time. We don't need to keep going. But if you want to read the rest of this solution, try and do the rest of it at home. It will foreshadow everything we do next time in class. Wednesday. All right. Sounds good. Oh my gosh, I'm tired. I really appreciate the extra 5 minutes. Sorry about that. Oh my gosh. So tired.